Welcome to our third learning workshop for Chemistry 1405. It'll cover atomic structure and electron configuration. We're going to go ahead and dive right into it. Isotopes. So isotopes are basically, and you probably already know this, probably somewhat familiar to you by now, but isotopes effectively are atoms of an element that have different numbers of neutrons, but the same number of protons. And effectively what that means is that, so let's write down for some example. For examples, carbon has 3 isotopes. So there's 3 isotopes of carbon that are common. There's carbon 14, which is the one that's used for the radioactive tests, for radiocarbon dating and such. There's carbon 13, and this accounts for a small amount of the carbon come across, and there's carbon 12, and this is the most common. So carbon 12 is probably roughly 90%, actually it's closer to 99%, and this is about 1%, and then there's a fraction of a percent, a tiny fraction of a percent that's carbon 14. So I'm going to say much, is that a greater than or less than? I feel like that's the wrong sign. That's greater than. I'm going to delete that. Less than. Less than 1%. Much less than 1%. Okay, so what do these numbers mean? Well, in any isotope symbol, I'm going to go ahead and write a generic isotope symbol. X would be the symbol of the element, O for oxygen, C for carbon, Ba for barium. But the top number here is the mass number. It is the mass of, it's the mass of the isotopes. The top number is the mass number. And the bottom number is the atomic number. Bottom number is the atomic number. You have the mass number on top, and you have the atomic number on the bottom. Okay, so, well, the atomic number is basically the same as the number of protons, and the atomic number is also the same. It's on the periodic table. You can find it on the periodic table. Usually, what's a little bit confusing is that for any symbol on the periodic table, let's say, for example, you have carbon as your symbol, what you'll oftentimes see is you'll see the carbon listed here, the number 6 here, and then you'll have like a 12.0111 or something like that. Well, here's the thing. That is not how things are organized for isotope symbols. So, basically what you have to recognize here is that the top number here is the atomic number on the periodic table. And the atomic number is the number of electrons, or rather, it's the number of protons that the nucleus have. Because the number of protons does not change, outside of a nuclear reaction. The number of protons does not change. It's the number of protons that determines what element it is, how it behaves. If you change the number of protons, you change what the element is. Now the bottom number here is what's referred to as the average atomic mass. Notice how I showed you over here, this is 99%, this is 1%, and this is much less than 1%. If it was 100% carbon-12, then this would say 12.00000. But it's not 100% carbon-12. You have a little bit of carbon-13. And when you take the weighted average of all the different isotopes here, you end up getting this number, 12.011. And therefore, this number down here is the average atomic mass. And the average atomic mass is not the mass of any particular isotope, it's simply the average mass of all the isotopes put together. Okay, so back to isotope symbols. Now how do you figure out what the mass number is, or how do you figure out what the number of neutrons are? Well, there's this nice little equation you can use to calculate it. And that equation is this. So the mass is equal to the protons plus the neutrons. So for example, if I'm looking at carbon 14, so let's say if I take this, if I'm looking at carbon 14 now, I know the mass is 14. If I want to solve for the number of neutrons there, I could simply say, okay, well, it's 14 for the mass. The protons is 6 because the atomic number of carbon's always 6. I have to figure out what the neutrons are. I'll just put N for the symbol there. Well, that's pretty easy to do. All I have to do is subtract 6 from both sides. And if I subtract 6 from both sides, I solve for N. And the neutrons for carbon 14 happens to be 8. So 8 neutrons and 6 protons. Now in a neutral atom, the number of protons and the number of electrons are the same. So for a neutral atom of carbon, the protons are 6 and the electrons are 6. Okay. But what about if it's not neutral? Okay. What about if it's not neutral? Well, if it's not neutral, then we have to look at use another formula, a different formula, and that would be this one. The charge, and you could also logically reason this out, but the charge is equal to the protons minus electrons. Why do we do protons minus electrons? Well, basically, protons are positive, electrons are negative. So the number of protons, which represents the number of positive charges, and the negative number of electrons, which represents the total negative charge, if I add those together, I get the total charge of the molecule. So, for example, I have a element of chlorine, or I have chlorine here, and chlorine, let's say it has a -1 charge, okay? Well, I could figure out how many protons and electrons it has simply by plugging it into this little formula here, if I wanted to. So the charge is -1. The protons for chlorine is 17, minus the electrons. Well, 17 minus 1 gives you -1. 17 minus what gives you -1? Well, in this case, what I could do is I could just add e to both sides and add 1 to both sides, and basically what I would get is the e has to be 18. 17 minus 18 gives you -1. So I can determine the number of electrons from a charged particle like this using this equation. So these two equations are useful for helping you determine the number of protons, neutrons, and electrons. The charge is equal to protons minus electrons, and the mass is equal to the protons plus neutrons. That makes sense so far? Any questions? We all good? Okay. In that case, let's go ahead and I'm going to uh, share a little bit. There we go. That'll work. In fact, actually, I just realized I'm going to drop it into the old file system. No, I'm not. I lied. I'm not going to do that. I'm going to share it directly with you. Okay, let's see. Oh, come now. Let's not be difficult. Ah, here we go. All right. So, for example, let's do a couple of these and see how we do. Okay. So it says copper 66. So what is the symbol? You'll notice that when an isotope name is given, it's oftentimes given as the name of the element with a number afterwards. The number afterwards is always the mass number. That's what this is always. This number afterwards, this is the mass number. That's 66. Okay. So if I draw a symbol, actually, I'm going to cheat here. I'm going to switch to something because I want to draw on this. Paste. Okay. I want to draw on this. I'm going to change what I'm sharing. There we go. Okay. So the symbol, copper 66. So the symbol for copper is Cu. And because the mass number is 66, I'm going to put that 66 up here. Now, what is the number of protons in a copper atom? Where could I go to find that? Yeah, 29. And that's from the periodic table, right? So copper has 29 as an atomic number. Well, the atomic number, remember, is the number of protons. And since the number of protons in a neutral atom, which this is the same as the number of electrons, I have 29 here. The atomic number, of course, is 29. And the mass number, of course, is 66. Now, how many neutrons are present in this particular isotope? How many neutrons are present? 37, absolutely. Exactly, 66 minus 29. Because mass minus the number of protons is going to give you the neutrons. Neutrons plus protons gives you the mass. So, 37, absolutely. Uh, Let's do... Ooh, I think that's a fun one. Let's do number 8. I'm going to actually cut this out. Select. Let's do number 8. And number 8 gives us the atomic number, and it gives us the mass number. Atomic number and the mass number. Let's solve for the rest of it. So what I'd like you to do is I want to have you guys help me out. Go ahead and solve for the mass number for me. Or rather, solve for the other things, the isotope name and the symbol. Most specifically, let's just actually focus on the symbol because that will pretty much mean that you understand it. So I want you to write the symbol for the element represented with this atomic number and this mass number. Anybody got it yet? Oh, you got it. Okay. What do you have? All right. So what are we looking at?
Symbol, the symbol is Se. It is
So the element
AD
symbol is
Se. Do you hear
Symbol
me?
is Se. So this is, whoops, this is
Se.
selenium.
Yeah. Yes. Se, and is the proton
So
is
symbol is
34.
selenium.
Yes.
The
Proton is
protons are
34.
34.
The NO is 46
Electrons are 34.
or 46. E is 34.
And neutrons are 46. And what
Yeah.
number goes on the top right of the top left of the symbol, the
It's
Se
80
symbol? 80.
and 30. No, sorry, sorry. Oh,
Oh,
yeah.
no, no problem.
No, no. Yes, correct. Yes, yes, yes.
And
The top
is
one is the
34.
80,
Yeah, excellent.
and the bottom
And that would just be called
bottom is
selenium,
34. The bottom 34. Yeah. Am I right?
selenium 80. Excellent. Well done.
Oh, okay. Selenium. Let's see.
Well done. Now, I'm not sure if I, yes, you're absolutely right. Excellent. Okay, well, very well done. Very well done. Um, so let's dig into this electron configuration stuff. Um, because this is actually one of the more confusing topics, but it does not have to be. The first thing I want to do is I want to share with you a very special periodic table that I made. And this particular periodic table is so cool because it's specific for electron configurations. And call it actually the periodic table for electron configuration. So let me go ahead and I'm going to get the link and I'm going to paste it into the chat and you can pop it open and save it. This is the electron configuration. So the periodic table for electron configuration is super useful because you can use this to figure out what the electron configuration is a lot easier if you use the periodic table as a roadmap for electron configuration. So use the periodic table for a roadmap for electron configuration to make your life a lot easier. Let me go ahead and pop this in here. And I want to show you how you can do this. So one of the things that you'll see is, and I'll cut this out. Um, so the periodic table, each of box in the periodic table represents a place for one electron to be. Okay, a place for one electron to fit in, so to speak. Um, and you can read the periodic table for electron configuration just like you would a book. You start at the top left, and then just read the first line, and then you go down to the next line, and then you go left to right until you get to the end, and then you go to the next line until you get to the atom you're looking for. So let's do a couple of examples and kind of see how this pattern works. It's actually super helpful. So let's say, for example, I was wanting to do the electron configuration for, say, nitrogen. Okay, so nitrogen, here's nitrogen, okay? So I start at the beginning, and I know I have to fill up the first energy level before I fill up the second energy level. So this is 1s2, 1s, and since there's two boxes, 1, 2, that means I can fit two electrons in the 1s orbital, or 1s subshell rather. And so this is 1s2. But after this, you notice there's nothing after this if I go across. So that means I have to go to the next line. I'll go to the 2. And so then once again, it's still in the s blocks. That means I'm filling up s orbitals. And so this is going to be 2s. And once again, I have two boxes, two places for electrons to be. So I have two electrons. So 1s2, 2s2. Okay. Then from there, I go across. This is still the second row, but it's the p block. So this is 2p. 2p. Now I have to fill up every place I need until I get all the electrons that I need for nitrogen. Well, nitrogen has a total of 7 electrons. I've already filled up 2 in S and 2 in the 1s and 2 in the 2s. Now I'm at 2p. I have to fill up 1, 2, 3 more boxes. So this is going to be 2p3. And so therefore this is going to be the electron configuration for nitrogen. 1s2, 2s2, 2p3. 2p3. Does that make sense? Now, if this is stuff that you already know or that you don't need to go over, please let me know. I can move past this and skip to something else.
Hi, Michael.
Yes?
Mr. Mike. Why did you fill out like 2P3? Can you repeat one more time? Because I'm not quite clear about that.
Oh, sure, no problem. So this is the second energy level. This is still the second energy level.
Mm-hmm.
And I have to fill up all the electrons until I get to the atom that I'm looking for. In this case, the atom I'm looking for is nitrogen.
Yes.
Well, so I filled up the 1s2.
Mm-hmm.
So I start from the beginning, and then I went to the 2s2, so 2 places for that, and
Mm-hmm.
then I go across. Well, now that I'm in the p block, this is the p block over here.
Mm-hmm.
This represents the filling of p orbitals. I have to fill up all of the places until I get to nitrogen. So I fill up 3. And so now you see that I actually have a total of 7 electrons. 1, 2, 3, 4, 5, 6, 7. Nitrogen has 7 electrons, and this is showing where each of those 7 electrons is.
Oh, I see.
Does that make sense?
Oh, so the nitrogen is you stop where you looking for, right?
Exactly, exactly.
Okay, so the nitrogen is the symbol with an N because you put them the Ni, so I thought it's like
Oh, sorry. This
nickel.
is not this is not Ni. This is supposed to be an N with 2 dots.
Oh, and
My
with
bad.
two dot, I would thought it's what a nickel. I was like, and then because the nickel is what a 28.
Yes,
No, that's why I don't understand about 2p3. So I understand because you stop where we're looking for until the nitrogen.
exactly.
I got that. All right. Thank you, sir.
Cool. Yeah, no problem. So let's say if you're doing sulfur, okay? So let's jump ahead to sulfur. And let's see if you're doing sulfur. Okay, so this is the element that I want to get to, the one right here.
Yes.
I still have to fill up everything from the very beginning until I get to sulfur. So
Oh,
I still would need to do the 1s2.
okay.
I would still need to do the 2s2.
Uh-huh.
But when I get to 2p, I'm not going to stop at 2p3. I'm going to have to continue to fill this up. I'm going to have to fill up every place that I
Okay.
can in the 2p subshell. So that's
2p3.
6
2p.
places.
Yeah.
Yeah, so 2p6. After that, I have to go to the next line, which is 3. So over here, I have 3, and so this is 3s2. So that's going to be 3s2.
Okay.
And then after that, I go across to the next place, which is in this case, I follow the numbers after 12 is 13. So here's aluminum. I have to fill this up. This is still the third energy level, and this is the P block. So that's I fill up 1, 2, 3, and then I have to fill up the fourth one, which is the sulfur. So that gives me 3p4.
3p4. Oh, I got it.
Does that make sense?
Yes, sir.
So I'm just filling up the pattern. I'm filling up using the electron configuration or using the periodic table as my roadmap. I fill up starting from the very beginning. I fill up every orbital until I get to the atom that I'm looking for. Does that make sense? Cool. All right. So now, at this point, I want to talk about why is it that we end up seeing in this. You notice that you might have seen this little sign in the D block. It says D block drop 1 energy level. That means if this says 4, that this over here, this is going to be the 3D. Well, why is that the 3D? That seems kind of weird. Why would we do that? Well, it comes down to this, and I'm actually going to draw you a little picture here. It's going to be fun. It's going to be fun because it's kind of a cool picture, but I'm going to have to zoom out and stretch my map a little bit here. I'm going to zoom back in. Okay. So let's do the electron configuration for, I don't know. What do you say we do it? Yeah, let's do it for scandium. Why not? We'll do the electron configuration for scandium. Okay, SC. Okay. So maybe you guys can help me with this one. What do I start with? What do I start with? What do I start the electron configuration with? What orbital am I going to fill up first? Yeah, 1s2, very good. So I'm going to start with 1s2. After that, what comes next? 2s2, very good. After that, what comes next? 2p6, very good. And then 3s2, very good. All right, 3p6, very good, excellent. You guys are on top of this. What comes after 3p6? 4s2, and then lastly, I saw something. Not 4D. When you go into the D block, you end up having to drop an energy level. Actually, it's a 3D. 3D1. And you might be like, well, why do you have to drop an energy level? That seems weird. Well, I could just tell you to do it, but I want to explain to you why. Okay, so let's take a look at why this is the case. I'm going to draw you some pictures, okay? And before I do that, I want to actually kind of explain a couple things real quick to you. You might have seen this, you might not have, but s orbitals are roughly spherical shaped, okay? So this is an s orbital, and I like to think of it as a sphere, so I like sphere. S for sphere. P orbitals are shaped kind of like this. And I think that kind of looks like a peanut. So, which is appropriate because it's P. So I'm going to say it's P orbital, and it's shaped like a peanut. Now D orbitals are a little bit more fancy. So D orbital is kind of shaped like this. Okay, so this is a D orbital. And I think it kind of, well, if I could draw better, it would look like a daisy. I'm going to say daisy. D orbital for daisy. You could also say D for double dumbbell, but D for daisy. And then the last type of orbital that you really actually may or may not even be expected to know what it looks like, but it's effectively has 4 nodes and 8 lobes, and it kind of looks like this. It's a 3-dimensional monstrosity. It looks kind of like that. That's the F orbital. And this is the highest energy of the orbitals. And the F orbital, I'd say it kind of looks like a fountain. fountains up. You can say it looks like a fountain. So sphere, peanut, daisy, and fountain. Okay, so I'm going to draw you a picture of a scandium atom, okay? I'm going to draw you a picture of a scandium atom. First, I'm going to actually move these guys, straighten it up a little bit, put them right here. I'm going to draw you a picture of a scandium atom. We'll start with the nucleus. Okay, we got a nucleus here. Here's your scandium atom. It has all sorts of little protons, neutrons, and they're all packed together in this tight little, neat little nucleus, okay? All right, first things first. I have a 1s orbital. S orbitals are roughly spherical, and I can almost draw. All right, so we have one electron here, and yeah, maybe one electron here, and that's our 1s orbital. Great. But now here's the thing. Now, for the second energy level, I now have a 2s orbital. So it's roughly the same shape as the 1s orbital, but it is further away from the nucleus. So I have 2 electrons in this orbital. Each orbital can only hold 2 electrons. Now here's the interesting thing about the p orbital. Why are there 6 electrons that can be there? Well, the reason is because the p orbital actually has 3 different orientations. This is still in the second energy level, so I'm going to make it the same color. But the p orbital can either be up and down, side, side, or back, front. So this is it going in the back. I can't draw three-dimensionally. I'm sorry. I'm terrible at that. But yes. And so each one of those orbitals, each one of those different orientations is a different orbital, a different pathway that electrons can be in. And so therefore, each one of them can hold 2 electrons. So I can have 2 electrons in this side, side one. I can have 2 electrons in this up, down one. And I can have 2 electrons in this in, out p orbital. Okay. Well, now, if you count the total number of electrons here, I now have 10 electrons. Okay. I've filled up. I've taken care of this, this, and this. Well, now I have 3s. So let's do a blue for the next one. So the 3 is like that. And I know, I'm sorry, I'm terrible at drawing. So that's a 3s2, and I'm going to put a couple electrons here. One here, one here. And then I have a 3p. Well, the 3p looks like this. One. And then, of course, the in-out pattern. Okay. So now it's getting complicated. And then 3p, there's 3 different orientations, and each one can have 2 electrons. So I'm going to put those electrons in here. 1, 2 for the in-out pattern. 2 for the side-side. 2 for the up-down one. So now, here's the thing. There is a 3D, because the numbers here, the 3s, the 3p, the 3d, the number here, the 3, tells you how far it is from the nucleus, roughly. Okay? And so the 3d is still the same distance from the nucleus, so I'm still going to draw it in blue, but look at what it is. It looks kind of like this. I'm just going to draw one of them. Actually, 5 different orientations for the 3D. So if you're looking at this complex pattern, there's a lot of traffic here. There's a lot of electrons all over the place here. It is not easy for the electron to dodge and weave so many other electrons being this close to the nucleus. So it could either do that, it could either fill up the 3D, or it could choose to go around. And it turns out that it's a lower energy to simply go around. The lower energy to simply go around. So that's why the 4s will fill up before the 3d. And the 4s, these would be your valence electrons. They're your outermost electrons. This would not be a valence electron. The 3d is not a valence electron because it's still an inner shell electron, but it's higher energy. It's higher energy because it requires more energy to weave around in this complicated pathway in the 3D location. And so that's why always the 4s comes before the 3D, the 5s comes before the 4D, and so on and so forth. You never actually fill up the 3D until after you fill up the outer S. Now, of course, if you were trying to compare the 3D to the 4P, well, the 4P still has to contend with all this traffic, and it's a more complicated pathway, but it also is farther away from the nucleus. So it actually ends up being lower energy to do the 3D than it does to do the 4P. That's why it doesn't just go from 4S to 4P and skip 3D altogether. If I was to show you an energy diagram, it would probably look something like this. Okay, so energy increases going up. This is energy, the big E, okay? So let's say I have a 1s orbital here. This is a 1s orbital. The 2s would be right about here, let's say. I'll make sure you can all still see what I'm doing. Okay, good. 2s, right about there. Where is it? Okay. 3s is here. 4s is here. And then like maybe a 5s here, okay? All right, but the 2p is actually here. Lower energy than the 3s, but significantly more than the 2s. And then once again, the 3p is going to be like right here. Use your 3p. But the 3d has 5 possible orbitals. Look at where they are. The 3d would be right here. Notice that it is just slightly higher than the 4s. It's a little bit higher energy than the 4s. Not a whole lot, but enough so that the 4s is actually lower energy, which is why the 4s gets filled first. Because it's balancing those two things. You can be higher energy by being farther away from the nucleus, or you can be higher energy by having a more complex orbital pathway. D is more complex than P, which is more complex than S. So there's a trade-off there. Turns out by the time you get to the D, 3D is so complex that it actually is more, it requires more energy than a 4s orbital. Does that make sense? I thought that might be helpful. I really want to open this up to your questions at this point. If you have any questions over, so we've gone over configuration and we've gone over isotope notation, but I really want to focus on those questions that you have relating to your classes to make this as helpful to you as possible. Is there anything that you would like me to go over, any questions that you have that I could help you with? Since I'm already here, and I know some of you will be covering this, let me just do a quick condensed electron configuration because it's actually super easy. So if we look at scandium here, you'll see that uh, instead of writing the entire electron configuration, we can actually use what's known as condensed electron configuration, which means we start with the previous noble gas. So in the case of scandium here, the previous noble gas is going to be krypton, or rather, here's scandium. The noble gas that comes before 21 is 18. That would be argon. So what I can do for scandium then is I can start with argon in brackets. I would say argon, Ar, and I put a little 18 to indicate the number of electrons that are filled up to that point. And then I go, well, what comes after argon? Well, after 18 comes 19, which means I'm in the 4s region. So then I just continue from there, and it's 4s2, 3d1. So that's condensed electron configuration. That's the condensed electron configuration for scandium, or noble gas notation. It's a quicker and easier way to find the electron configuration for an element. So instead of like, let's say for example, if you had something like cesium, cesium is right here, okay? So cesium's right there. Instead of starting with 1s2 and just going 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, etc., I can just start with the previous noble gas, and I can be like, okay, well, the previous noble gas to cesium is 54, or xenon. I'll just do xenon, 54, and then after that, it's the 6s orbital, so I just say 6s1. And that would be my noble gas notation electron configuration for cesium. Pretty easy, right? Okay. What about, so let's go ahead and do just one last one. Let's do lead. Let's do lead, because if you can do lead, then you're going to be solid for pretty much everything. So lead is over here. I have PB, PB82, so I have lead. I can go ahead and do I'll actually clear out some of this bottom stuff here. Cuts. Okay. So the previous noble gas to lead is xenon, 54. So I'll start with xenon, Xe, 54. And then I will go 6s2, because that's what comes next. The xenon is at the end of the 5th row. This is the end of the 5th energy level. So I go to the 6th one to start out the next one. 6s2. I have to fill this up. 6s2. But notice this is a 56 and this is a 71. So after 6s2, I don't go to the D block. I have to go down here. This is the F block. And when I go to the F block, for the same reasons that I dropped one energy level in the D block, I dropped two energy levels in the F block. I was previously in 6, but going down to the F block, that means this is going to be a 4F. I dropped two energy levels. This is 4F. So I'll do 4F, and I fill up everything all the way over. There we go. And that's 14 if I count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 4F14. And at the end I hit 70. Well, after 70 is 71. So I go from here back up to the D block, where I go, and so it's what it would be expected that this would be the sixth energy level, but remember I dropped one for the D block, so this is going to be the 5D. And then I fill that up completely. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 5D10. And then I have to fill up until I get to lead. So that's 80. So here's 81. So this is going to go back up to 6 because this is the P block again. So I go back to normal. And 6P1, 2. 6P2. Now, how many valence electrons does this? How many valence electrons does an atom of lead have? Remember, the valence electrons are the outermost electrons. How many valence electrons does this atom of lead have? It's going to actually be only 4 because the highest energy level electrons are going to be your 6s and your 6p. Those are the ones that are going to be furthest away from the nucleus. Those are going to be your outermost electrons. And so as a result, those are the ones that are going to interact with the other elements around them. So these are the ones that are important for bonding. These are your valence electrons, your outermost electrons. That's a total of 4 valence electrons. Well, thank you very much for coming. We'll see you next week. Have a great night. Bye-bye.